Usually when we sit down to do one of these deep dives, we're looking at a success story.
Right.
We talk about the big breakthrough, the eureka moment, like the apple falling on Newton's head. We really love a winner.
Yeah, well, it's human nature, right? I mean,
Yeah.
we want to hear about the person who cracked the code.
Exactly. But today we are doing the complete opposite. We are looking at what is arguably the most famous, most expensive, and frankly most catastrophic failure in the history of physics.
Oh, it was a crisis. A total, absolute crisis.
A failure so bad, it basically broke the classical model of the universe.
Just completely shattered it.
And forced Einstein to invent relativity just to, pick up the pieces.
We are talking, of course, about the Michelson-Morley experiment of 1887.
We are. But here is the hook for today's deep dive and why I was so excited when I saw this stack of sources.
It's a really unique angle.
It really is. So we have this series of analytical blog posts. They have this fantastic title, Einstein's Slacker 100. And this is the wild part. Alongside the blog, we have a literal Python script.
Yeah, technical script for a Blender 3D simulation tool.
Yeah.
Which is not your usual physics paper material.
Not at all. It's called the Symmetric Spacetime Michelson Interferometer. And the argument across all these sources is simple but kind of mind-blowing. They argue that Michelson and Morley didn't fail because of their machine.
No, the machine was incredibly precise.
Right. They failed because of their accounting.
And just to be crystal clear for you listening, we don't mean financial accounting.
No, they didn't lose the receipts for the mirrors.
Right, we're talking about speed accounting.
Yes. The argument is that for well over 100 years, we've been treating this as a deep physics mystery, like a failure to detect this magical ether.
When really it might just be a geometry error.
Exactly, a failure to balance the books.
It sounds provocative, I know. But when you actually look at the geometry, specifically through the lens of what the sources call step 4 deviation shooting, it starts to make an uncomfortable amount of sense.
So our mission today is to unpack this. We're going to talk about hunting traps, we're going to talk about Pythagorean embezzlement, and we'll explain why light is strictly prohibited from double spending its paycheck.
I love that analogy.
But before we get to the solution, let's set the scene for the listeners. 1887, Cleveland, Ohio.
Right.
Two guys in a basement with a lot of mirrors. What exactly were they trying to do?
So you really have to put yourself in the headspace of a 19th century physicist. At this point, everyone knew light was a wave. That wasn't up for debate. It was settled science.
Okay.
And if you have a wave, basic logic dictates you need a medium for it to wave through.
Right, like sound needs air to travel.
Exactly. Ocean swells need water. You can't have a wave and a whole lot of nothing.
So they needed a space ocean.
A space ocean. They hypothesized this invisible cosmic medium called the luminiferous ether. They figured it just filled the entire universe.
Everywhere.
Everywhere. And since the Earth is spinning and, orbiting the sun at this tremendous clip, something like 30 kilometers per second, we must be just plowing through this ether.
Like a boat speeding through a quiet lake.
Precisely. And if you're on a fast boat, you feel a wind, right? So Michelson and Morley thought, if we can measure this ether wind blowing against the Earth, we can prove the ether exists.
And we can measure our speed through it.
Exactly.
And the machine they built to do this, the interferometer, it was basically designed to race two beams of light. One goes forward, fighting into the wind, and the other goes sideways, across the wind.
It's the classic swimmer in a river math problem. If you swim upstream against the current and back, it should mathematically take longer than swimming across the current and back.
Because the current fights you more.
Right. So they fully expected the light fighting the ether wind to be delayed.
And a result?
Zero.
Nothing.
Absolutely nothing. The beams arrived at the exact same time. It was as if the Earth was standing perfectly still in the cosmos. It was dubbed the null result. It really shouldn't have happened, but it did.
Okay, so that's the standard history book version, right? We look for the ether, we didn't find it, oops.
Right, the great failure.
But let's bring in our source material now, because the Einstein's slacker analysis introduces a metaphor that totally reframed this entire experiment for me.
The deviation shooting.
Yes, deviation shooting.
This is a really, really powerful way to visualize the mistake they made. The source asks us to just stop thinking about waves and water for a second and start thinking about a hunter, a shooter, and a target.
Okay, paint the picture for me.
So the source breaks this down into different steps of complexity. We start with step 3, which is the classical assumption. This is what Michelson thought he was doing.
Okay.
Imagine you were standing in a field. You are completely stationary. and you see a target, maybe a clay pigeon, flying across the sky.
Okay, I'm the shooter. I'm standing still on the ground. The target is moving left to right.
If you want to hit that moving target, you obviously can't aim at where it is right now.
Right, I have to aim at where it's going to be. I have to lead the target.
Exactly. You calculate the lead. You aim at a specific point in empty space ahead of it.
Yeah.
And here's the crucial part. When you pull the trigger, your bullet travels at its full speed toward that interception point.
Because I'm not moving.
Right. You're using 100% of the bullet's velocity to close that gap.
Makes total sense. That's just standard everyday physics.
That is step 3. And that is exactly how Michelson modeled his experiment. He thought, I am on Earth. I need to shoot a light beam up to a mirror. The mirror is moving because the Earth is moving through space.
So I just need to aim the light diagonally to catch the mirror.
Yes, he was just leading the mirror.
But the source argues this was the fatal mistake. Because Michelson wasn't actually standing still in a field. Michelson was in step 4.
Step 4, deviation shooting.
Yeah.
This is where it gets real.
Right.
In step 4, the shooter is moving too. Imagine you're on a train doing 100 miles an hour. You have a gun, and you are trying to shoot a target that is also on the train with you.
Okay, so the whole system is moving. Me, the gun, the target, we're all in it together.
Now think about the bullet. If you aim at that target on the train, your bullet has to do 2 things simultaneously.
Sure.
It has to travel toward the target, sure, but it also has to keep moving sideways at 100 miles an hour just to stay inside the train.
Right, because if it didn't keep that sideways momentum, the train would just leave it behind. It would smash into the back wall of the train car.
Precisely. And this right here is the trap. Michelson assumed that the sideways motion, the speed of the Earth, and the bullet speed, the light were separate accounts.
He thought he could just add them up.
He thought the geometry was additive. He completely missed that light operates on a very strict, fixed budget.
Yes. This is the part that really clicked for me in the reading, the speed budget.
It's brilliant.
The source actually calls it Pythagoras' budget allocation, which sounds a bit like something from a horrific IRS audit, but it's actually really intuitive.
It's the most important concept to grasp if you want to understand why the experiment, quote-unquote, failed. Light has a fixed salary. Let's call it 1.0 c. That represents the absolute speed of light.
1.0, that's your hard limit. You can't go into debt. You can't get a loan from a bank. That is all the speed you have to spend.
Exactly. Now, let's go back to our train, or in Michelson's case, the Earth moving through space. Let's say the apparatus is moving at 10% of the speed of light, so 0.1 c.
Okay, we're zooming along at 0.1.
For that light beam to simply exist inside your moving apparatus to look like it's going straight up to a mirror and back down to you, it must travel sideways at 0.1 c.
It has to match the speed of the Earth just to stay in the room.
It has to pay the toll.
It has to pay the toll. So you take your $1 budget, you subtract the 10 cents you just spent on sideways motion.
And you think you have 90 cents left, right?
Right. I'd assume I have 0.9 left for the vertical motion.
Well, it's not quite simple subtraction because physics loves triangles. It's the Pythagorean theorem. A squared plus b squared equals c squared.
Ah, right.
But the conceptual budget is exactly the same. The hypotenuse, the total speed, is rigidly capped at 1.0. If one side of the triangle, the sideways motion, gets longer.
The other side, the vertical motion, absolutely must get shorter.
Right, you cannot lengthen the hypotenuse. It's fixed by the laws of the universe.
But Michelson thought the hypotenuse could grow.
He did. He thought, I'll use my full 1.0 speed to go up, and the 0.1 sideways speed is just extra momentum carried from the source. He effectively calculated a total speed of roughly 1.005.
He's trying to spend $1.50 when he only had $1 in his pocket.
That is the accounting fraud. He was double spending.
So let's look at the actual numbers provided in the source. If we do the math properly, no cheating the universe, and we spend that 0.1 sideways, how much do we genuinely have left for the vertical trip?
If you run the Pythagorean calculation, the square root of 1 squared minus 0.1 squared, you get about 0.995.
Okay, 0.995. That's close to 1, but it is absolutely not 1.
It's definitely not. And that is the key to the whole century-long mystery. The light is moving slower vertically than Michelson expected, not because of an ether wind, not because of friction.
But simply because it had to spend some of its speed budget just to keep up with the moving Earth.
This is what the sources refer to as time accounting.
Time accounting.
Yes, if you spend velocity on covering space, moving sideways, you have less velocity available for, well, for covering the vertical distance in the expected time.
Michelson was obsessing over a delay on the horizontal arm of his experiment.
Right, the swimmer going upstream.
But he completely missed that the vertical arm was also being slowed down by this Pythagorean budget cut.
It's so counterintuitive, though, because we humans are used to incredibly slow speeds. If I'm walking down the aisle of an airplane, I don't feel like I'm walking slower just because the plane is moving at 500 miles an hour.
Because compared to the speed of light, walking is practically free.
Exactly. The budget cut is so infinitesimally small at human speeds that we just ignore it. But when you start moving at planetary speeds or relativistic speeds, that tax gets really heavy.
To really visualize this tax, the source material uses a train thought experiment. And I think we need to walk through that because it shatters that everyday human intuition that leads us astray.
Definitely. So visualize that train again, moving at 0.1 c. We have a laser pointer on the floor pointing straight up, and we have a mirror directly on the ceiling.
Got it. Floor to ceiling, let's say it's exactly 10 feet. Train moving fast.
In the classical view, Michelson's step 3 view, you point the laser slightly forward to account for the train's motion, you fire, and you expect it to hit the mirror in, say, exactly 10 nanoseconds.
Because I assume the light is traveling up at full speed, I assume I'm getting my money's worth.
But we know about the budget now. The light is paying a 10% tax to move sideways with the train. So it's actually only moving up at 99.5% speed.
So after 10 nanoseconds, where's the light actually?
It's at the perfectly right spot. Horizontally, it kept up with the train just fine. But vertically, it's not at 10 feet, it's at 9.95 feet.
It hasn't reached the ceiling yet.
It is a missed shot. The source calls this the step 4 reality. If you rely on the classical assumption, you think you've hit the target on time. In reality, the light is lagging behind.
It takes longer to reach the ceiling than you calculated.
And that taking longer looks exactly like the light has slowed down.
Which brings us perfectly to the second source we have today, the blender simulation.
Yes, the Python script.
It's called the Symmetric Spacetime Michelson Interferometer. And honestly, I love that we are analyzing code comments and 3D software to understand 19th century physics. It feels very modern.
It's a brilliant way to verify the logic. The code is designed to draw these light paths in 3D space. It creates a literal visual proof of what we just discussed with the train.
The documentation mentions a red line and a blue line. Walk us through what we're looking at there.
So you run the simulation. The red line represents the classic expectation. It shoots up from the moving apparatus, hits the ceiling, and comes back down.
And it assumes an infinite budget.
Right. It assumes the hypotenuse can grow. It's the line Michelson thought he was measuring.
The fantasy line.
The fantasy line. Now, the blue line represents the relativistic reality. It rigorously obeys the speed budget. As you turn up the speed of the apparatus and the software, you see the blue line start to detach from the red line.
It physically lags behind on the screen.
Visually, yes. The blue line becomes shorter vertically. It creates a flatter, wider triangle. It shows you visually that the light simply cannot climb as fast when it's forced to move sideways.
There's a really cool feature in the code called the time accounting panel. I kind of want one of these for my car dashboard.
I think it would be a very confusing dashboard for a daily commute.
Probably. But in the simulation, it puts the math right in your face. It shows field speed equals 1.0. That's the absolute speed of light.
And right next to it, it calculates the local apparent speed.
And that's the speed measured inside the moving ship.
Right. And as you increase the ship's speed slider, you watch that local apparent speed number drop. 0.9, 0.95, 0.90.
It visually proves that from the perspective of the moving observer, the components of velocity are literally shrinking.
It builds a Minkowski spacetime visualization right before your eyes. And this leads to a bit of a philosophical trap, doesn't it? The source mentions the difference between the map and the territory.
The map is not the territory. It's a classic semantic warning, but here it's purely geometric. Michelson was stuck in the coordinate system trap.
Explain what you mean by that.
Well, he was calculating everything from his own map, his own perspective, the moving self. When you were on the train holding a ruler, the ruler looks totally normal to you. Your watch ticks normally. You don't feel the budget cut because you and your instruments are all paying the exact same tax.
We are all embezzling speed together.
Exactly. You only see the discrepancy if you look at the absolute field, the territory, or in the simulation, what they call the spheroid surface.
So let's bring this all back to that basement in Cleveland in 1887. Michelson and Morley are staring at their data. They see zero.
They expected a shift, and they got a big fat zero. Why is that?
Because the math balanced itself out perfectly.
Hmm.
And this is the real beauty of it. Michelson expected a delay on the horizontal arm because of the wind.
Right, fighting the current.
But he completely ignored the delay on the vertical arm caused by the speed budget.
And those two delays
Were geometrically identical.
Wow.
The slowdown he didn't account for on the vertical trip exactly matched the resistance he expected on the horizontal trip. The light followed the rules perfectly on both arms.
They arrived back at the same time, not because the Earth was stopped, but because the geometry of light speed is symmetric.
So the experiment didn't actually fail.
It proved the speed budget.
It was a wildly successful demonstration of speed accounting. They just didn't know how to read the balance sheet yet. They thought the books didn't balance, but really they just missed a line item.
This really reframes the whole concept of time dilation for me. Usually when we hear about relativity, it sounds like, I don't know, magic.
Yeah, time slows down. It sounds like a sci-fi movie.
But phrased this way, with the budget.
It's just bookkeeping.
It's just bookkeeping. You can't spend money you don't have. If you spend speed on motion, you literally cannot spend it on time.
That is the core takeaway from these sources.
Yeah.
Relativity isn't about some mysterious warping magic. It's about the strict conservation of a fixed budget.
If you move fast through space, you move slow through time.
Yeah.
Not because of magic, but because of geometry.
And classical physics failed because it tried to double spend.
It wrote a check that the universe bounced. So before we wrap up, I have to ask. We aren't moving at point 1c. You and I aren't on a spaceship doing relativistic speeds.
True.
Why should you, the listener, who is maybe driving to work right now or folding laundry, care about step 4 deviation shooting?
Well, technically, we are on a spaceship.
Grr.
We are on a spinning rock, orbiting a star, which is orbiting a supermassive black hole, which is drifting through the cosmos. We are moving.
Which means our local apparent speed is never quite 100%.
We are always paying a tax to the universe just to exist in motion. Your watch is ticking slightly slower than a watch floating in deep, empty, stationary space.
That brings us right back to that time accounting panel from the Blender software.
I love that image so much.
Just imagine you had that panel floating in front of you right now. You're sitting in your chair, maybe you're commuting, maybe just washing dishes. You feel like you're stationary. You feel like your speed budget is completely full.
But if you could actually see the dashboard of your true velocity through the cosmos,
how much of your budget is currently being spent just to sit still on this spinning rock?
that's a staggering thought.
And here is the real question to leave you with, building on what we learned today. If you could hit the brakes, if you could stop moving through space entirely, would you suddenly start moving faster through time?
That is the ultimate question. Would you age faster if you stood truly still?
I'm going to be thinking about that all week. Huge thanks to the creators of the Einstein Slacker blog and the symmetric space-time code for this totally mind-bending perspective.
Keep looking at the map, but please don't forget the territory.
Thanks for taking this deep dive with us. We'll see you next time.